Hello everybody and welcome to chapter 7.3 of Advanced Functions. We're still continuing with tools and strategies for solving exponential logarithmic expressions and equations, but today we're actually going to be finishing the laws you need to know for solving and expressing different logarithmic expressions and equations. So let's get started on that. So today we're going to be covering the product and the quotient laws of logarithms. So first we're going to talk about what the product law is, then we're going to talk about what the quotient law is, and I'm also going to do like a little bit of a derivation for both of them. It's really not that long, so don't worry. So let's talk about the product law of logarithms. The product law is, again, just an amazing tool we can use to solve various logarithmic expressions. So this is what the law states. Log of base b of m of n times n is equals to log of m to the base of b plus log of n to the base of b. And again, here's our restrictions. We know that a log function has to have the base greater than 0, but it cannot equal to 1. And in this case, b has to be greater than 0 and n has to be equal to greater than 0. Because if we have either one of them as 0, we would be having a lot of issues essentially with how this turns out to be. Because again, this times this would be 0, so log of 0 to the base of b would equal to a number plus 0. That really doesn't make any sense, right? So that's why these restrictions are there. So the three things you could do with it are listed out. The first way you could use it is to evaluate logarithms. For example, you're given these three numbers here, right? So what you could do, you could type each one of them into your calculator and then add them all together, which would take a long time. Like these would be decimal places, right? Like these would not be proper numbers, and so you would have a rough estimate of what these would equal to. However, using the product law, we simply just plug these into the equation. So we have three arguments here, so this would be m times n times O. So then we would have 8 times 2 times 9 all to the base of 12. As you notice here, it has to be the same base. You cannot use this if you have different bases. However, if the bases are the same, you're good to go. Multiply everything within the bracket, and so we get 144. And then look at that. Log of 144 to the base of 12. We know that 12 to the power of 2 is 144, and so our answer is 2. That was pretty easy. Following that kind of idea, we could also use it to simplify complex logarithmic equations. So now we can't really solve it because we'll be dealing with variables, but we could get it very nice and compact so we can actually analyze it. So let's see. Here is our long equation here. And first what I would do is express all the square roots as a power. We know if we have a square root, that's the same as multiplying or putting m to the power of 1 over half. And so that's what I did over here. From this point, we know that if we have two exponential expressions divided by one another, we could simply just subtract the exponents from one another. So now we get 1 over 2 minus 3. Then for here, we actually have something to the power of something, again to the power of something. When that's the case, you simply multiply the two exponents together, and so we get 7 over 2. Now, what I'd like to do is use the power rule that we discussed before and just plug that in. So again, we just carry over the exponent and put it in the front. So now we have no exponent here. I didn't change anything for this step because I want to focus on this here. You can now open these brackets. Maybe you did that in the last step, but either way you should get negative 5 over 2. Again, now we have an exponent. We could drag it to the other side. and so we get our equation here. As you can see, we're just having two multiples of log of m adding to one another, and so negative 5 over 2 plus 7 over 2 is the same as 2 over 2 log of m. Again, we know that 2 over 2 is the same as 1, and so our answer is simply log of m. As you can see here, we went a really long way, right, to determining what this equals to, and that's why this rule or this law is so powerful. Lastly, we can also reverse the process we just did, and then write something like log of m as the addition of two logarithms. I didn't want to do it with a really complex expression like this, because in reality you're probably not going to be doing as much. But here, for example, I was given this, and so I was figuring out what does 384 multiply to, or what is it a product of. So I figured out it was the same thing as 6 times 64. Then using the product law, we know that's just the sum of the two logarithms. And so we do that, then we can identify that this over here is simply equals to 1. And so our final answer is this. As you can see, it is pretty simple. You just need to memorize this equation. If you're good with that, we could now talk about the quotient law. The quotient law is super similar to the product rule, the product law. And essentially, now instead of dealing with multiplication and the sums, we're dealing with the division and the subtraction of logarithms. Yeah, sorry, I just want to fix that. So the quotient law states the following. You have something in the middle, two things divided by one another, and that is equals to log of the first thing minus log of the second thing. As you can see, they're super similar. Like, this was plus and this is now minus. So multiplication is related to the addition and the division is related to the subtraction. Again, our restraints for this is exactly the same. Here we can actually easily figure out why n cannot equal to 0 because it's in the denominator, right? So here, this again would be impossible now, so that's cool. But yeah, for m is greater than 0, again, this would be log of 0 is equals to log of 0 minus a value, which wouldn't make sense either. So similarly to the product law, we can now use the quotient law to perform the same functions. So for example, before we used the product law to evaluate logarithms, so we could use the quotient law to evaluate logarithms. So if we were given an equation like this, we know when we're subtracting two logarithms, we're simply just dividing the two numbers in the brackets. So the first one is being divided by the second one. So we get 320 divided by 5, put that into your calculator, and you find out it's 64. We know that 4 and 64 are closely related, right? We actually know that 4 to the power 3 is 64. Therefore, our answer is 3. Again, we can also use the quotient law to simplify complex logarithmic equations like we did before. So here, we're given this equation, or this expression. If we have two things minus each other, it's the same as dividing them under the common logarithm, or under a common logarithm. So value number 1 divided by value number 2, we get this. We can easily factor x squared plus 7x plus 12, which is x plus 4, x plus 3. The values cancel out, right? And now we get log of x plus 4. The important thing here is to remember your restrictions. Just like we did in rational functions, if we were to divide or cancel these values out, we still have to account for the restrictions that we had beforehand. So in this equation here, our restrictions would be that x cannot equal to -3. And so for this equation here, we know that x has to be greater or equal to -4, but x also cannot equal to 3 because -3 because it's not defined for that region. Again, this should be fairly familiar to you because we've already gone over this. Lastly, we can also talk about how to write a single logarithm as a difference of logarithms. So for example, if we're given this here, we could write it as the following. You can also go the extra mile and try to make it more visually appealing and more understandable to a general audience, because the square root of b is the same as b to the power of 1/2, and so using the power rule, we just bring that over here, and so we get our full answer. Now, if you're good with that, we can actually talk about how to derive the product law and the quotient law. Again, this is going to be super simple, and you will see it on this slide. So how many steps do we have? We have 6 steps for each of them. That should immediately tell you this is not a complex derivation. It's nowhere near as long or as complicated as some of the ones we've done before. For example, for the compound angle formula or any of the trig identities we've done. So for the product law, we have it here. You probably noticed for all of the proofs, we let a constant equal to our log. So here I chose m is equals to log of x to the base of b, and n is equals to log of y to the base of b. So now we can rewrite this here, right, or these here as exponents. If we do that, we know that our answer is within the bracket, b is our base still, and our exponent is our old answer. And so we get b to the power of m is equals to x, and b to the power of n is equals to y. We know that the product law deals with the product of 2 numbers or more, so why don't we multiply them? So we get b of m times b to the power of n. And we know that when we're multiplying 2 exponents or 2 numbers with the same base, we just add their exponents. And so that's what we've done here. We get b to the power of m plus n. Now I would just substituted in our values for b to the power of m and b to the power of n, and so we get x times y is equals to b to the power of m plus n. Rewriting this in logarithmic form, we get log of x times y of base b is equals to m plus n. Again, our base is still our base, our exponent is now our answer, and our old answer is now in the brackets. Substituting the values for m and n back into our equation, we get our product law. As you can see, it wasn't difficult, pretty simple. We can use this exact procedure to find out the quotient law. Again, let's follow the same steps. M is equals to the log of x, and n is equals to the log of y. So again, writing that in exponential form, we get these guys. Now that we're dealing with the quotient, we're dividing 2 numbers, right? So we could say b to the power of m divided by b to the power of n. And so when we're dividing 2 numbers that have the same base, we simply just subtract their exponents from one another, and so we get b to the power of m minus n. Again, substituting the values in for b to the power of m and b to the power of n, we get x divided by y is equals to b to the power of m minus n. Rewriting this in logarithmic form, pretty simple, we've done this so many times. And now substituting back our values for m and n, we get our quotient law. As you can see, these 2 derivations are super simple. And so I'd really recommend you doing this at least once, because if you do it, you'll most likely remember it. We had to prove these on one of our tests, but again, they're pretty simple, so it wasn't worth a lot of marks. For today, here's the homework. It is not difficult. It is simply plug and play into these equations here. The only one that might be difficult and I'm not even sure if I assigned it, is the word problems. The word problems, you need to actually try to understand what's happening, but at the same time, it's still going to be plug and play. You're going to plug in the values into either one of the product or the quotient laws, and then solve for an answer. So we only have 6, and then like around 12, 15 max questions. It shouldn't take you that long. And once you do that, you'll be good to go with everything you need to know for how to manipulate logarithmic functions and expressions. So hopefully you've had a lot of fun today. I'll be trying to upload more frequently, but school has started for me, and so it might get a little bit more busy. Again, I'll try my hardest to finish the course in the next 2 weeks, so that by October, or the start of October, the first week, we have everything done, and you guys can prepare in case you have advanced functions in semester 1 or your quadrimester. But yeah, either way, I hope you enjoyed today's lesson. Bye bye!